Okay, let's get started. We're gonna cover a lot today. Okay, so we went over Galileo, we went over Newton. Newton got figured out mathematically how the solar system works, and came up with an explanation as to why the stars are in a fixed location. But he also did tons of other stuff. One of the things he did was he invented a new type of telescope that uses mirrors instead of lenses, and that greatly enhanced our ability to see things in the night sky. We still use the old, they still at this time use the old fashioned big lenses, but most of the discoveries come from these parabolic mirrors, right? So we already talked about Galileo discovering the moons and everything. I push buttons. Sometimes you get some secrets. All that do is part, you know. Aha. I should have been able to figure that out.
Now we know next.
Yeah, now I know this. So Galileo used a telescope to see these moons floating around Jupiter and saw mountains and valleys on the moon. There they are. Okay, perfect. Thank you. But Galileo did other things too. The moons. What did he do? First see the moons of Jupiter. That was like 1609, 10, something like that. But he kept on viewing the heavens, and in 1610, later on in 1610, he saw peculiar things around Saturn. He described them as ears around the planet, or as love handles around the planet. He in 1610 he saw these, but in 1612 they were gone. What happened? These things disappeared, right? Things aren't supposed to happen like that. Well, 1616, a few years later, they're back. And this is Galileo's interpreted his sketch now of what they look like. You know, I'm only guessing. Maybe Zach knows the answer to this. Certainly, as the years progressed, Galileo got better and better at making telescopes. And by 1616, he probably had a pretty good telescope, and so he could these love handles could be a little bit better discerned in what he was viewing. But then comes along Christian Hingis. Galileo's telescope was about 30x, 30 times your eyesight. Christian Hingis built a bigger telescope in 1659 and determined that indeed these were rings that surrounded the planet. Wow, mysterious rings. This whole new discovery as to what's going on here. Excuse me. So now, we know Mercury, Venus, of course, Earth, Mars, Jupiter, Saturn, all of these things are visible to the naked eye. But with telescopes, we've been able to see the moons orbiting Jupiter and the rings of Saturn. So we're discovering more and more things, right? Next planet up is Uranus. This is a very interesting discovery. It was actually observed as early as Galileo. He plotted this star in his star charts that when he looked at the telescope, but these outer planets move very slowly, and so it looks like it's fixed to Galileo. And so Galileo did not consider this to be the star. Along comes William Herschel. I have to be careful now as I'm going through some of this description, because some of these people I'm going to be talking about are assigned to are assigned as part of the in-class presentations. So I'm going to give some information, but not all the information, because I want to give you guys something to talk about when it comes along. But anyway, Herschel, very famous astronomer at the time, was viewing different objects, and he looks at Uranus and he increases the power on his telescope. So you can increase the power by changing the eyepiece. And one of the ways to determine if the object you're looking at is a star, because stars are very far away, and certainly at the time, even up until today's time, when we look at a star through a telescope, it's just a point, it's just a dot, right? So if I increase the magnification, it's still a dot, it's still a point, right? Herschel looked at Uranus, increased the power, and the dot got a little bit bigger. It's like, whoa, this is not a star, it's a comet. This is a comet coming into the solar system. I've discovered a new comet. The Herschels, both William and Caroline, were looking for lots of new things in the sky. One of the main things that they were hunting for was new comets. And so, okay, I found a comet. He increased the magnification again and again. Found a new, the object got bigger. So, okay, this is something that's in close to us. And in his telescope at the time, it was a little bit hazy, right? Lots of comets, right? They're hazy and close to us. So he reported this through the Royal Society as a discovery of a new comet. Okay, but his colleagues, Anders Johann Lexell, computed the orbit. So now we have this object, we know where it is, we can look at it through the telescope, very accurately measure its position as good as we can. And then based on those position measurements, we can compute the orbit. It's a circular orbit or near circular orbit, right? Comets have big elliptical orbits, right? So maybe this isn't a comet, maybe it's something else. And so the controversy goes on and on and on until finally, Herschel is convinced that indeed what he found and mislabeled was a new star. He makes the statement, by the observations of the most eminent astronomers in Europe, it appears that the new star, which I had the honor of pointing out to them on March 1781, is the primary planet of our solar system, right? So he's admitting that he misinterpreted what he saw in his telescope, but he's claiming he's laying claim to having found it, right? So he doesn't want to give up that notoriety. So indeed, it's going to be his. So now we got to name the thing, right? Well, of course, we all know Uranus is what the name ends up being. Remember, Uranus was the god of the sky, right? Uranus and Gaia. This is a famous picture where Kronos cut off the genitals of his father, threw him into the ocean. But naming, okay. No. So since Herschel discovered it, he starts laying claim to naming this thing. He wants to name it after King George, who, oh, by the way, because he found a new planet. So, this is since the beginning of time, we had the inner planets and Jupiter and Saturn. Now we have one more planet. This is a huge discovery. And King George honored Williams or Herschel with making him an astronomer, a paid astronomer. He paid him 200 pounds a year, and the 200 pounds was conditional on him moving his telescope to Windsor Castle, where the royal family lived. And part of the deal was the royal family could look through the telescope when they wanted to. Right? So he gets hired as the first royal astronomer. And so, of course, he wants to name the thing after King George. That doesn't fly too well with people around Europe. Of course, the people who computed the orbit and did some of the foundational work, thought that maybe it's not that um, maybe the honor of naming shouldn't go exclusively to Herschel, and so different names are batted around, and finally the name of Jupiter is settled on. The reason for that is the British astronomer named Bondi said that Uranus is the Greek god of the sky, just as Saturn is the father of Jupiter in Roman religion or Roman mythology. Then Uranus is really the father of Saturn, because Uranus obviously is the beginning of the Greek god chain. So this nomenclature was set up. We're going to use Greek and Roman mythology to name these planets. So finally, Uranus is picked, and it works out. So Uranus is just barely visible with the naked eye. Good word, yeah. Uranus's brightness is like around 5.6 or 7. What number is that?
Yeah,
Yeah,
you can be down to 6.
it's dim as 6.1, but as bright as about 5.7 or so.
Yeah.
Which is visible with the naked eye, not my naked eye, because I don't see anymore.
I've never seen.
You've never seen it? In fact, can usually pick out in the sky. But this is the last planet that is visible by the naked eye. What do we mean visible by the naked eye? So here is the apparent magnitude of stars. Apparent meaning we label or we give stars a brightness relative to other stars. So it's the brightness of star A apparent to star B, right? So the bigger the number, the more positive the number, the dimmer it is. The more negative the number, smaller the number, the brighter it is. So you can see down there the sun is minus 26, right? Well, what does the scale mean? This apparent scale was set by by the Greeks, and the way they split the stars up into 6 categories, with brightness of 1 being very bright and brightness of 6 being very dim. The difference between 1 and 2 is about half as bright. So the difference between 2 and 3 is another half. So the difference between 1 and 3, factor of 4, right? So you see how this is kind of a logarithmic scale, and it's based on the human eye. Okay, bright stars, Betelgeuse, real bright star. Alpha Centauri is another bright star. Sirius, you see here Venus is 4.4. We can see about to 6 binocular limits, about 10. 1 meter telescope about 19. The 2.4 meter telescope that you guys were at has tracked things down to magnitude 24, which is really, really dim. It's dimmer than they should be able to track with that size of telescope. But the reason they can do it is, one, the sky here in this part of Mexico is very, very dark sky, which is good if you're looking for a bright point. So we enjoy very dark skies. And the camera that they use to integrate the signal, as long as they know where to point the telescope, the camera will integrate the signal, and so they can see these very, very dim objects. And a lot of it has to do with Dillon and Eileen's capabilities of running the telescope, knowing how this thing works. So it's a combination of the location, the apparatus, and the person running the telescope. Interesting thing about apparent magnitudes and the brightness of stars is the Roman legion. Roman soldiers were given a test. If you look at the Big Dipper, there's actually two stars, Alcor and Mizar. Can you see the two stars there? Yeah. I don't think I did. I might have been able to do it 20 years ago. My eyes are starting to fail. If you were a Roman soldier and you could distinguish that there was two stars in this part of the Big Dipper, you were given the honor of being an archer. So you have a good vision, right? I don't know if that was really something you wanted, right? Where are the archers? Archers are like the first group of people when the two armies would come into battle. The archers would be out front, so that'd be a pretty tough position. What you might want is the other test that was given to Roman soldiers was looking at Pleiades, right? So Orion's belt's pretty easy to identify. Betelgeuse is that bright star. We have this belt. The Pleiades are up there in the corner. If you could see 7 stars, you'll see there's 6 in this picture. But if you could see 7 stars and you're in the Roman legion, you could be an archer or you could be a scout. If I had to choose, I'd want to be a scout, right? Because you're not in harm's way. You go out and, well, you could be in harm's way as a scout. But I think you got a better chance of being a scout than being on the front line as an archer. Anyway, you could have your choice. So let's see, where are we? Okay, so now we have these telescopes. People are looking all over the place, and the next thing that gets discovered is asteroids, right? And so there's a number of asteroid belts around the solar system. The main asteroid belt is in between Mars and Jupiter. This is leftover stuff from when the solar system was forming. We're going to talk about how the solar system forms here in just a little bit. But the first asteroid we discovered, pretty big asteroid, Ceres, was named Ceres. Ceres, remember Ceres and Persephone? The daughter that ate the pomegranate seeds and had to stay in Hades 6 months out of the year. Ceres is the goddess of agriculture. The first asteroid was discovered, thought it was a planet, but then the determination was made that no, this asteroid wasn't big enough. As much as they tried to magnify the image at that time that Ceres was discovered, it was still a point of light. So it wasn't big enough and didn't make it in as as a planet. We'll talk about how we define planets, and we'll get to Pluto here in just a minute. So the asteroid belts are discovered. Next is Neptune. Okay, so again, Galileo did see Neptune and plotted it in his star catalog. He saw it in 1612 and in 1613. But at that time, Neptune was just going into retrograde, right? So we talked about retrograde motion earlier in the semester because the inner planet, that Earth is an inner planet, it moves faster than, let's go this way. The Earth moves faster than the outer planets. It can, because of the relative motion between the Earth and the outer planets, that outer planet can at one time be seen to be going from east to west, but then back up and go west to east, and then turn around and go back east to west, right? So when Galileo was looking at Neptune, it was just going into retrograde, which meant it had stopped going east to west and was starting to go west to east, so it meant it was stationary, right? So it really didn't look like a star. So Galileo assumed that this was just another ordinary star, right? But Alexis Bobbard calculated the orbit. So when did he do this? 1812. Okay, so we're up to the early 1800s. he was calculating the orbit of Uranus. Okay. So Alexis Bouvard is calculating the orbit. So the mathematicians are really getting into this, astronomy stuff. So you calculate the orbit, which then allows astronomers to find it, right? Here's what the orbit is, here's the equation for the orbit. 6 months from now, if I want to go look at Uranus, I calculate, the coordinates from the orbit and I point my telescope in that direction. Turns out that his calculation, was good, but not quite good enough. Okay, the orbit is getting perturbed. Now, the orbit of Uranus is being perturbed. Something is pulling it out of its orbit, out of the normal path, just a little bit, right? This becomes very interesting, right? Because this is now the first evidence that there's another planet out there. There's something else to be found. To me, this is really the birth of modern science, in that we are using mathematical models to make predictions when those mathematical models don't agree with our observations. And as always, we got to go back and find another explanation. But now it's not just one person and one telescope, right? It's the whole community doing this. So Bouvard calculates the orbit of Uranus. Uranus's location is not quite exact. So here comes the British, right? John Couch Adams, a mathematician, says, okay, we can find that new planet if I have some really good data. So he goes to James Chalice, who is the head of the Cambridge Observatory, and Adams says, hey, I need some really good data so we can take a shot at finding this new planet. George Avery is the royal astronomer at the time at the Cambridge Observatory, and so he provides some data to Adams so he could do the calculations. Avery at the time was in the Lucasian chair at Cambridge. That was the chair that Newton occupied when he was at Cambridge. So the British come up with a predicted new planet, and they give its general whereabouts. So here's where we think the new planet should be. At the same time, a guy from France, French mathematician, Verrier, collects data as well, and he does his own calculation as to where this new planet should be. So we have two competing estimates of the planet's location. And again, this is how science works today. We make estimates of particles, particle masses, all these different things, and then we go off and try and find them. Well, it was two German astronomers that ended up finding this thing. Johann Gottfried Galle and his student Heinrich de Arist. Let's see. The student, where do I have this? The student at the observatory suggested to Galle that they could compare recent drawn charts of the sky in the region where Leverrier had made his prediction. So the student says, hey, we've been making some measurements in this area. By measurements, what they do is they point the telescope and then they sketch where everything is located. And so he says, we could continue doing that, and then we could compare the location of the dots that we see in the telescope to see if they're moving. If they're fixed, they're stars. If they're moving, they're planets. The student suggested this, and in that evening, they started the hunt, and that very night, they found the planet. Okay, so immediately found, and what they found was it was within 1% of Leverrier's prediction, and within 10% of Adams' prediction. So, both pretty good, but Leverrier seemed to be more accurate. Of course, controversy comes up, who gets credit for the discovery? And there was a lot of, you can imagine, the British versus the French trying to figure out who is a rightful person to get credit for the discovery. At the time, the conclusion comes to that. It looks like the two of them are pretty much a discoverers. So both the two of them, Leverrier and Adams, get credit for discovering Neptune. As time went on, and much more recently, back I think it was in the 60s, 1960s, another investigation was done into this, and the royal papers were in both Britain and France were scrutinized very closely, and the conclusion came to that Leverrier should get full credit for the discovery. So nowadays we give Leverrier the credit for the discovery. The new planet. Okay, where do we go next? Oh, we got to name the thing, right? The Germans, they're the ones who actually physically found it. They want to call planet Janus, Roman god. The British suggests Oceanus, Greek god. The French, Leverrier, suggests Neptune, Roman god. This gets battled around back and forth quite a bit, and eventually, really the ultimate authority into the naming at this time was what becomes universally accepted, right? So there's competing factions within Europe and the United Kingdom, well, I guess England at the time, England and Europe, and eventually one of the names sticks, and that's how it's done. Now we have a very sophisticated voting process that takes place, right? Okay, Pluto. So Pluto next to be discovered. This is in the 1900s. Get up speed here. Percival Lowell is a wealthy Bostonian, and with his money, he decides to build an observatory in Flagstaff, Arizona. So this Lowell Observatory, which is very active till today, not far from here. That's an easy drive. Well, not a fairly easy drive. This is a picture, I think, of Lowell himself looking through the big telescope that they built in 1894. They started a project looking for what's called Planet X, right? So again, we look at the orbit of some of the objects in the solar system, and those orbits seem to suggest that there's something else perturbing their motion, and so maybe there's another planet out there. Lowell did numerous searches, actually did take some photographic images. At this point, we have photographic plates, and there are some of those early work. Pluto was there, but it was not recognized as an object. It was still thought to be a star. Along comes a young, 23-year-old Clyde Tombaugh. Clyde Tombaugh was a young man who didn't have a whole lot of formal education at the time, but had built his own telescope, and this telescope caught the eye of the director of the Lowell Observatory. Silver is his name, and so he hired young Clyde Tombaugh to help with this project, right? They used a technique called the blink comparator. So here is, this is an asteroid, this isn't Pluto. but this shows you how this works. So you see here, these are fixed stars. They're comparing an image taken one night with an image taken a few nights later. And you see here that obviously this thing is moving relative to the fixed stars. So this blink comparator is something that gets used extensively in astronomy. And Tombaugh is given the given the credit for discovering Pluto. Tombaugh, a big connection here to New Mexico. Tombaugh left Lowell Observatory and was a professor at Mexico State University in Las Cruces for a long time. And as a matter of fact, Eileen and Bill both went to school down in Las Cruces, and I think it was Eileen that shared an office with Tombaugh when she was working on her PhD. So anyway, they both know Clyde Tombaugh. So okay, we got to name this critter, and this gets a little controversial. The discovery of the new planet is headline news around the world. The Lowell Observatory, since they discovered it, everyone agrees that they get the right to name it. They get thousands of suggestions, and the wife of Lowell. Lowell has since passed away. His wife is kind of not real happy that her husband spent all their money on this observatory, but she wants to name. She figures she gets to name it since it was their money that was used to build the observatory, and so she wants to name it Zeus. Her name is Constable. She wants to name it Zeus. Then she changed her mind. She said, no, let's name it Percival after her husband. And then she changed her mind again and said, no, let's name it Constant after me. Right? So she wanted to name the planet after herself. They came up, they decided to have a big competition, broadcasted around the world. Said, please give us a name for the new planet. And there was an 11-year-old schoolgirl from Oxford, England, who was very interested in classical mythology. Her grandfather was a librarian at Oxford, and so she had access to this mythology. And she came up with a suggestion of Pluto, not the dog, but the Greek god. And Pluto is ruler of the underworld, right? So we have Neptune, which is the sea. We have Uranus, the sky. We have Pluto, the underworld, right? The suggestions came in. It was put to a vote by the staff at the Lowell Observatory at the time. Unanimously picked Pluto as the name. Right? What would happen to Pluto? Right? Or Pluto got kicked out of the solar system, right? Well, or at least it's not what we call a major planet. So why? What is the story behind Pluto, right? So the International Astronomical Union has 3 criteria to be considered a full-size planet. Okay, one is it's got to orbit around the sun. Okay, that's not too hard. 2, it has sufficient mass to assume hydrostatic equilibrium. So a lot of the asteroids are odd shaped like cigars or different type of shapes. If you're a big enough planet, you have enough internal gravity that everything kind of comes into a sphere, right? It doesn't have to be a perfect sphere. Certainly the Earth isn't a perfect sphere, but at least there's a nearly a round shape. And then third, the object has cleared out its neighborhood of objects around it. So as it orbits around the sun, it impacts, kicks out, pulls out the junk that's surrounding it. That's where Pluto fits, right? One is Pluto's orbit isn't in the plane of the other planets, and so there's not the junk that it sees is really in the ecliptic, in the plane of the planets, and so that junk doesn't get cleared out, and so that's the fake Pluto, is that it doesn't clear its surrounding, and so by that definition, it's considered a minor planet, and that's also fits for the asteroids, things like Sirius that I mentioned earlier. It's not big enough to clear its own pathway as well. Okay, so we've got the solar system. This is what we think it. We're not going to add anything else, probably, unless some mysterious new planet pops up. How did it get here? How did it form? Okay, so there's been lots of theories over the past few centuries. Immanuel Kant came up with the first theory, that gaseous mass theory. So primordial cold cloud, right? So there's cold cloud that you see in the upper left-hand corner of the picture. Gravity starts to pull things together as the matter in the cloud gets pulled together. It starts impacting each other. Impacts cause heat, and that the temperature increases, and that causes the cloud to start to spin. The increase in temperature causes the gas to melt, and the spinning gas starts to contract. Rings are ejected to form the planets, and what's in the center becomes the sun. All that sounds pretty good, except this cloud, this sits there and starts to coalesce. These things like cloud starts to spin. Well, where did the angular momentum come from for it to start to spin, right? So Immanuel Kant's first theory, or his theory of how the solar system forms, violates angular momentum, so we don't like that, right? So there's a nebular hypothesis. This comes from Laplace, the famous guy, the famous mathematician of the Laplace transform, right? So we start with a slow rotating hot gas. How it gets there, we don't know, but we do have a rotating hot gas. The gas cools, the cloud shrinks. As the cloud shrinks, the rotation rate increases. This is like the ice skater that pulls her arms in, she goes faster, and the rings make the planets, right? Unfortunately, if we look at this, at Laplace's theory, and apply it to our solar system, the sun is not rotating fast enough to explain or to support this theory, right? So there's this planetesimal hypothesis, Chamberlain and Malott. So there's you have a cold sun, a big clump of junk, and a star passes near the sun and pulls out the planet. So you have a cold sun that's gravitationally trying to heat up. As that's happening, a big massive object comes by and gravitationally pulls out stuff from the sun, and that stuff forms the planets. Again, how do the planets start to rotate around the sun? So we're violating angular momentum in this case. This theory, proposed in 1905, was added to in 1925 by Rayleigh Jeans Jeffries, but still they don't have it violates angular momentum, and this theory doesn't seem to hold water. So finally, here is our current theory of how we think the solar system was formed. We start with the cloud, a slow cloud, rotating gas of interstellar dust, right? So not too hard to think that, and we'll get to the Big Bang where in a few weeks where all this stuff is thrown into the universe. We have lots of hydrogen, helium atoms. They start to gravitationally attract each other. So we have this big rotating cloud. about 4.5 billion years ago, because that's the age of our solar system, a shock wave passes through this cloud. Where does the shock wave come from? Well, supernova, a star exploded, a nearby star exploded, and this shock wave permeates through the universe. As that shock wave goes through our cloud, it causes the cloud to collapse, which increases its rotation rate, right? So it gets a kick from a supernova that went off somewhere nearby. Sun forms in the center, leftover matter clumps up, the sun starts to produce heat, the nearby gas is burned off of the inner planets, and the outer planets are beyond the freeze line, and so we have the gaseous planets. So this is how we think the solar system was formed. We had this big cloud, shock wave goes through the cloud, causes it to start to contract and spin faster, and inner planets were once gaseous, but that gets burned off from the sun. The outer planets, planets after Mars, are beyond the freezing point, and so they're gaseous planets. Not everything in the cloud for our solar system turned into a planet. That's why we have these asteroid belts, particularly the one between Mars and Jupiter. That's one theory. Another theory is that a planet did try and form there, but it got smashed up, pulled apart by the gravitational attraction of Jupiter. But nonetheless, all of these theories are based on the fact that supernova shockwave caused the process, right? Other things that have been discovered, and Herschel Williams and his sister discovered a lot of nebula. Nebula are named after Greek god, what's her name? Nebulae, which is Latinized to nebula. Later on, we found lots of different types of nebula, diffuse planetary star clusters, galaxies. So this is all of this whole line of discoveries that take place in the after Galileo in the 1700s, 1800s. So bigger telescopes. Oops. I'll do this too. Lost the notes. There we go. Bigger telescopes mean we can discover more things. But at some point, we've kind of reached the limit of what we can discover by just looking through the telescope and taking images of that. Okay. So again, this is a picture of one of the bigger telescopes that the Walkers used, and they used it to map out the Milky Way. Okay. But now, the next big breakthrough is spectroscopy. So we look at an image, we take a photograph, and then we can calculate exactly where things are. But what is the light that arrives to us? What is it composed of? Bunsen-Burner and Kirchhoff looked at the light from a flame and passed it through a prism and saw that there was peculiar things in the spectrum. There was spectral lines, right? So if the light from the burner went through the prism, they saw bright lights. Right? If light from the sun passes through the gas of the burner, they see dim lights. They see shadows, not lights. What's going on?
If you use a prism to spread out white light, you will see a continuous spectrum of colors. If you first pass the light through a cool gas, you will see dark lines or gaps in the spectrum. This is called an absorption spectrum because the dark lines are created when the cool gas absorbs these specific colors from the light passing through. If you heat up this gas until it starts to glow, it will produce an emission spectrum. Bright lines of color in exactly the same place as the dark lines in the absorption spectrum. These lines are the specific colors this gas emits when heated. Every element produces a unique set of lines, thereby making it possible to identify elements by looking at spectra. Thus, we can discover what the sun and other stars are made of by looking at the lines in their spectra. By studying these lines, we can figure out these distant objects' temperature, speed, distance, and age, among other things.
Wow. What did you just say?
By studying these lines, we can figure out these distant objects' temperature, speed, distance, and age, among other things.
So we can figure out what the star's made out of, what the temperature is, how far away it is, how fast it's moving, and how old it is. Just by looking at these spectral lines. It's a fingerprint, right? So the hydrogen, helium, oxygen, water, all these different atoms and molecules give a very precise spectral line. Very, very accurate, right? And if the temperature is higher, then that spectral line gets shifted just a little bit. But we know from the signature of the spectral line, the fingerprint, that we are looking at hydrogen, and that hydrogen spectral line should be at exactly so many nanometers. It's a few nanometers off, we know, aha, it's a little bit hotter, or it's moving away from this, or it's moving toward this. So this new spectroscopy allows us to make all of these determinations of the light coming from stars. And what that allows us to do, so the spectral lines, it allows us to group the stars into different types of groups. So now we can study something that's very, very far away. So far away, we can't even see the size of it. We can just see it as a dot, but we can tell how far it is, how fast it's moving, what it's composed of, what the temperature is. And so all of these things become very useful in our identification of things that fill our universe. So that brings us up to about the end of the 1800s, the 19th century. And at that point, there's a very famous quote from Lord Kelvin, and I know this is assigned to somebody. I'll give the quote here, and then I won't say much more about Lord Kelvin. But Lord Kelvin made the determination, and I think it was a conference in 1900, there is nothing new to discover in physics. We're done, right? All that remains is to do more and more precise measurements. Let's just, all we're gonna do now is work out the details. Okay? Well, unfortunately, or fortunately, Lord Kelvin wasn't quite right. There's a few other things that were discovered since the turn of the century, things like quantum mechanics and relativity and a whole bunch of other stuff. Yeah, so this was at the British Association for the Advancement of Science, that's in 1900. So we'll hear more about Lord Kelvin in our student presentations, right? But here, end of the 1800s, going to the 1900s, these are the two big scientific questions, the two things they just need to work out the details, okay? One is how light travels through this luminiferous ether. We've heard discussion of that a little bit earlier, but we should be able to measure the presence of this ether as light passes through it. But the other is the radiation density versus wavelength issue. We're going to talk a lot more about that here in just a second. But anyway, you can see this black line is the observed line, and the red line is what the theory predicts out at larger wavelengths on the order of 200, 300, 400 nanometers. Or 1,000 nanometers. The theory predicts the observations quite well, but when we get in to smaller wavelengths, the prediction is terrible. Okay. So these are two problems that scientists are worried about. The first one, let's look at that one where we have that problem with at the low wavelengths. So the question is, what is light? What is heat? And what is the relationship between the two? What's the relationship between light and heat? Okay. Along comes Max Planck. So he studied under Kirchhoff. Kirchhoff was this guy, right? So Max Planck went to study with Kirchhoff. Kirchhoff said, in this field, most everything is already discovered. And all that remains is to fill in the holes, right? So everybody's taking Lord Kelvin's advice and saying, yeah, not much left, right? In 1894, Planck got a job working for the electric company. And back then they used DC power to power electric lights instead of gas lights. So they were just converting over to electricity. And the electric company wanted to know wanted to get the maximum amount of light from a light bulb with a minimum amount of energy, right? So how do we make light bulbs so that we get as much light as we can with producing the minimum or consuming the minimum amount of energy? This was the assignment to Max Planck. So at the time, the idea was Max Planck looked at what's called black body radiation. So if you take a hunk of metal that has a cavity inside the metal and you drill a hole, small pinhole, so you can look into the cavity, right? And then you heat the metal. As you heat the metal, we start seeing a glow coming from the inner cavity. That glow changes color as it gets hotter and hotter. Changing color means it changes wavelength, right? So this is what the experiment shows. So you look at different temperatures and you get a different peak in the wavelength of the inside the cavity, right? So this is essentially a plot of energy density versus wavelength inside the cavity. This is what the experiment gives us. Okay, classical theory says that the energy density should go as lambda to the -4th, which means you get this classical theory, this catastrophe at low wavelengths occurs. So Planck is trying to figure this out because he wants to figure out at what temperature do we get the most light. Now we want visible light, right? So we need to get somewhere in 400 to 500 nanometer range. So here's an explanation of what he found.
Where did quantum theory come from? It started not as a
Political ads. Oh, nice. Isn't that nice?
crazy idea, but with a light bulb. In the early 1890s, the German Bureau of Standards asked Max Planck how to make light bulbs more efficient so that they would give out the maximum light for the least electrical power. The first task Planck faced was to predict how much light a hot filament gives off. He knew that light consists of electromagnetic waves, with different colors of light carried by different frequency waves. The problem was to ensure that as much light as possible was given off by visible waves rather than ultraviolet or infrared. He tried to work out how much light of each color a hot object emits, but his predictions, based on electromagnetic theory, kept disagreeing with experiments. Instead, in what he later called an act of despair, he threw the existing theory out the window and worked backwards from experimental measurements. The data pointed him to a new rule of physics. Light waves carry energy only in packets, with high-frequency light consisting of large packets of energy and low-frequency light consisting of small packets of energy. The idea that light comes in packets, or quanta, may sound crazy, and it was at the time, but Einstein soon related it to a much more familiar problem: sharing. If you want to make a kid happy, give them a cookie. But if there are two kids and you only have one cookie, you'll only be able to cheer them up half as much. And if there are 4 or 8 or 1,600,000, you're not going to make them very happy at all if they have to share one cookie between them. In fact, if you have a room with infinitely many kids, but not infinitely many cookies, if you share the cookies evenly, each kid will only get an infinitesimally small crumb, and none of them will be cheered up. And they'll still eat all your cookies. The difference between light waves and kids is that you can't actually have infinitely many kids in a room. But because light waves come in all sizes, you can have arbitrarily small light waves, so you can fit infinitely many into a room. And then the light waves would consume all your cookies. I mean, energy. In fact, all these infinitesimal waves together would have an infinite capacity to absorb energy, and they'd suck all the heat out of anything you put in the room, instantly freezing the tea in your cup, or the sun, or even a supernova. Luckily, the universe doesn't work that way, because, as Planck guessed, the tiny high-frequency waves can only carry away energy in huge packets. They're like fussy kids who'll only accept exactly 37 cookies or 162,000 cookies, no more and no less. Because they're so picky, the high-frequency waves lose out, and most of the energy is carried away in lower frequency packets that are willing to take an equal share. This common average energy that the packets carry is in fact what we mean by temperature. So a higher temperature just means higher average energy, and thus by Planck's rule, a higher frequency of light emitted. That's why as an object gets hotter, it glows, first infrared, then red, yellow, white, hotter and hotter towards blue, violet, ultraviolet, and so on. Specifically, Planck's quantum theory of fussy light tells us that light bulb filaments should be heated to a temperature of about 3,200 Kelvin to ensure that most of the energy is emitted as visible waves. Much hotter, and we'd start tanning from the ultraviolet light. Actually, quantum physics has been staring us in the face since long before light bulbs and tanning beds. Human beings have been gazing into fires for millennia, with the color of the flames spelling out quantum all along.
Okay, so. Planck solves the mystery and comes up with a relationship between heat and light. So this is one of a burning question, right? What is the relationship between heat and light? Planck was not an astronomer, but he contributed this theory of light makes major advancements in the fields of astronomy, cosmology, and that kind of stuff. Some of the people that you've been assigned for your presentations, they may not have been astronomers, but the work that they did was a great contribution to astronomy. So that's what I want you to talk about. Oh, by the way, Planck knew Einstein quite well and encouraged him not to get involved in astronomy. Fortunately for Einstein, he decided to go ahead and do that anyway. So, how good is Planck's theory? Here is this solid line in this graph is the measurements. The crosses, stars, are the Planck's prediction. The uncertainty in the prediction is smaller than the little x's. So the uncertainty in the prediction matches the measurements to as good as we can measure. Okay. We call it the laws of thermodynamics. We don't call it the theory. Because it works. I mean, this is dead nuts on. If we can make some thermodynamic measurements, we can be very confident in the predictions that we draw from those measurements. This Planck's theory of quantized energy stirs a whole new branch of physics. Sorry, Lord Kelvin, you were wrong. And there's a number of conferences called Solvay conferences where physicists gather together in Europe to discuss this new fangled quantum theory. You see Albert Einstein is one of the people at the 1927 conference. Einstein never really accepted quantum theory. The reason is when you get down to that very small level, probability starts to take over. And there's a famous quote from Einstein where he says that God doesn't play dice with the universe, meaning that probability really shouldn't play a role in physics. Turns out he was wrong. It does play an important role. But you see all these very famous physicists, right? Max Planck, Marie Curie, Lorentz, Van Dirac. I mean, every one of these people is very, very famous. This Solvay conference, I don't know if I have the exact statistics. Let's see, like do here. Let's see. Of the 29 attendees to the 1927 Solvay conference, 29 attendees, 17 won Nobel prizes. There's one guy here. Then the reason I show this picture, this guy here, Irving Langmuir. Of course, Langmuir Lab is our Lightning Research Center here. Irving Langmuir was very much a part of the research that went on here at New Mexico Tech in the late 1950s, early 1960s. Irving Langmuir worked for General Electric and studied the atmosphere inside the light bulb, right? They wanted to make the filaments last as long as possible. And so he looked at the chemistry between the light and the atmosphere in there. To Langmuir's credit, what did he do? Let's see. He discovered atomic hydrogen, developed a theory of single layer chemistry, and published a seminal paper for the arrangements of atoms, the arrangement of electrons in atoms. And he won the Nobel Prize. And so he was invited to this conference. You see he has a cane here. He was an avid skier. He had traveled to Europe to attend the conference. While he was in Europe, he went skiing and injured himself. So you see him walking around on crutches. And oh, by the way, any of the film that you see at the Solvay conferences, when you see 8mm film, that 8mm film was taken by Irving Langmuir because General Electric, the company, had just obtained an 8mm camera, motion picture camera, something that was brand new, and so he was out using it. Solvay conferences. So anyway, this is a New Mexico Tech connection. Langmuir came here to study cloud seeding and lightning research. He was a very close colleague of E.J. Workman from Workman Center. Although later on in the relationship, Langmuir and Workman got into big arguments. And so Langmuir went back to New York where General Electric is. But Workman was smart enough, Langmuir Lab, which was funded by the National Science Foundation on a grant that Workman wrote. He, in the proposal, chose to name the lab after Langmuir, even though they were having a big quarrel. He used his name and his status as a Nobel laureate to get funding for the lab. So Workman was a good enough politician to know that even though they were having a fight, he could still abuse his name. Okay? So back to Max Planck. He came up with, here's the temperature your light bulb has to run at. And he showed Lord Kelvin was wrong. Another interesting, he got the Nobel Prize in 1918. Another interesting thing about Planck, who was a German, his youngest son, Erwin, participated in a failed attempt to assassinate Hitler, was caught and executed. Max Planck stayed in Germany during the war when most every other physicist fled Germany. The only two that stayed behind were Heisenberg and Planck. Planck stayed behind because of his son. His son had been arrested and was going through a long, protracted trial. Planck was very famous and thought he could use his world-renowned fame to save his son. Unfortunately, that was not the case, and his son was eventually executed. Okay, we have come to today's end. We are not going to have class on Thursday. Unfortunately, I'm out of town, and the time I'm out of town is when class is. So, but plus we're going to cash in some of the hours that we spent with Langmuir Lab on Thursday. But since there's no class on Thursday, You get to read 2 chapters, chapters 4 and 5, and then we'll have a quiz. Oops, that should not say the 7th. We'll have a quiz on next Tuesday. Let's fix this right now. What is Tuesday?
12.
The 12th? The 7th is my dad's birthday. He will be 97 years old. Okay, there we go. Read chapters 4 and 5, quiz on the 12th. Any late homework that you have, email directly to me. I will grade it myself. But when you do turn in late homework, I do take off a point for tardiness. The later it is, the more points I take off. So if you're late on homework, get it in as soon as you can, so I don't subtract too many points. Lateness. Any questions? We'll see you guys next Tuesday. Yeah, just on those 2 chapters. Yeah. Yeah, sure. You have a question?
Chronologically, going by current window born,
When they did.
and they did it. I just figured it's not gonna be, because.
Well,
I'll be
you
here
have-
at 14th, so I pretty much assumed that my 14th, so I'll be good.
Who do you got?
You have Frank. I gotta.
I'm gonna start doing that there, speech.
Oh, Fred Wood, I don't
Oh.
know where maximum. Yeah, Fred Wood, I already looked up when he was from,
Yeah,
So,
so he's the 19th century, yeah.
Yeah.
He's part of the big bang guys.
yeah.
Yeah, no, he's a cool guy.
I did like Church Street stuff, so I was like, okay, that's.
Zawicki.
Well,
He's my favorite guy. Zawicki was crazy.
well, this guy, I was like, I was reading it, like, towards later, it's like, he was trying to refute, like, the general, like, the widely accepted,
Fred Hoyle took a different tact against the accepted theory. He
Yeah.
tried to do everything he could to
dismantle it.
dismantle, yeah, so.
I'll see you.
Okay,
And
see
then-
ya.
That's next.
And then the next Thursday is when we start.
Yeah.
Yeah, but you won't be.
Yeah, I won't-
But you're gonna be gone when?
So I have to leave on the 13th, because I have to.
Oh, so you need to go on the 12th, or when do you get back?
I will be back, I'll be back that next Monday.
Oh, okay, so you can do it.
Oh, we're starting the next Tuesday,
Next Thursday.
next Thursday. Oh, we're starting next Thursday, start next Tuesday. No, who's? I gave you the wrong date. That's the 14th, okay, yeah, the 14th, I won't be here. So the 19th or the 21st, I'll be here.
Okay, so you'll be there for.
Yeah, I'll be there.
Okay.
I'll probably end, like, if I'm towards the end of
You're
year.
in towards the end.
Have a good week.
Two. What's up?
Oh, I was just hanging out.
Are you still, is that's your trailer, right, that's on the road to Water Canyon?
It was,
And then we moved again?
Yeah, it's so, it's
How
so
do you-
cool.
what, whose land is that horse land?
Yeah, that's first. So every 14 days or so, I have to,
You have to pull up stakes?
yeah, move 5 miles, but it got so cold Sunday night that I was like, you know what, I'm just gonna go to the rodeo grounds for a couple of days, because I have to move it to the grants on Thursday, that they go to Alabama. For comp.
Oh, okay.
I should be back Tuesday, but not shaking around time to light, what on my flight. So,
What conference though?
the AAPSO, it's like the American Variable Star.
Oh, cool.
I'm presenting some of, Dr. Davis.
Yeah.
Right, so,
She works with Michelle. Yeah.
Michelle's pretty fun to work with.
Yeah.
Is there anything that I can help out with like, if you you get late work that's graded or the,
Let me see how much late stuff's coming in.
okay,
There was only 2 or 3 that I graded, yesterday.
okay,
But other than that, I think we're good. I was, if, because I don't know what's going on, well, to be determined with, the president, like right now, there's a cabinet, I told him I wasn't gonna go to this class. But as we get into the student presentations, I may have to have you just go in class and then I can, watch the presentations from an opto video.
okay, okay. What's going on with yeah, I don't know if I'm able to ask, but, what's going on with the president meetings, so.
Well, you know, there's the search is going on for a new vice president.
Okay,
Yeah.
those are,
And I'm not one of them. But, with the president, with the president, the deal that he made to me, which is actually, I think. I'm gonna become what's called a presidential fellow, which we've never had one in New Mexico Tech before, but, so I'm an advisor to the president. So I'm in the cabinet, which is part of the decision-making process, but I don't have to worry about any of the compliance stuff. I don't have to do any of the personnel stuff. I don't have to do any of the compliance stuff. All I have to do is teach and advise the president when, you know, special assignments. for the president. So at first I was like, that's cool, right? But then the day after, well, the week, that was last week, that he informed me that that's what he wanted to do, and so I accepted it. He gave me 3 assignments in 1 week. So to do- I mean, it's not bad stuff, it's good stuff, right? But I'm like, holy crap,